moment, that part, and also you have one practical based on that. So we will take that. Okay. So are you going to see this presentation? Yeah, you probably seen this bending movements. I'm talking about the bending of beams. So this bending of beam or bending moment. So what do you mean by generally a beam? Okay, you know that generally we have you have a certain scale like this one. Okay, and you just apply a force in a such a way that okay it get bends. Okay, so it is just you apply forces at its end points, okay, and get it like a curvature of this kind of a shape to that. So what exactly happens here also, generally a beam when you define it has just similarly you consider it's a rectangular rod of uniform cross section or some circular or a rectangular cross section, okay, which length is remember is more or great compared to its thickness. Okay, so its thickness is a very small, okay, but its length is a large. So that's the beam you have. You have a beam or a column when you define, okay, so as geometrical length, okay, is more as compared to its thickness. That is the beam you have always. So when you say when you apply those forces and the beam that particular gate bends, okay, and you have this terminology called as a bending moment. Okay, so when a beam is fixed at one end and loaded at the other, it bends due to the moment of the load. Okay, so the plane is same. So what is that bending plane? So we called as those planes, okay, which got bends, called as a bending planes. And when a beam is what we say, it is similarly to the what when you apply a force, okay, and that's the what the restoring forces are developed, okay, and the body get deformed, okay, and deformation of that particular beam when you apply such a forces at a particular end. You say couple, like you have a force at one end, okay, and then the force perpendicular to that particular length arm you called as a couple. So similarly this kinds of forces, okay, because of you apply, and that equilibriumly the restoring forces are developed, okay, and that body get deformed. So remember that when you say that the restoring or the resisting couple, okay, that's the force acting on the length arm, you say that's the couple, that becomes equal, okay, and opposite to the bending couple, okay, that what they are in the plane of bending. So remember this is the bending moment here I am defining. Okay, so moment is a word which is coming because of the word that particular uh, restoring forces, that because of that body get deformed, okay, and there is a what the bending. So you look like what will be this the manner in which this you apply a force and that bending get applied. So you will see that this is the way you can see over here, okay, the cursor, yeah, this particular region, okay, this is which is not to be earlier, it is a word like a streamline. This portion should be a streamline, but it's now get bent and you have a what curvature, okay, and that is what you say that some portion or some filaments when you apply this torque or a couple, the filaments on the inner part, okay, that is we called as a concave side get shortened, okay, and when or a compress, while the outer face is becomes a what a lengthened or the extended. Okay, you can see in this particular figure this particular way, if the forces we are applying and that bending is occurs, okay, and that's what you say that some of the inner filament where the what you have what shortening of that, okay, that's the uh, filaments means we are talking about each and a lamina of those kinds of beam, okay, and the outer portion you say get extended, okay, and this the equilibrium you have. And these two portions you say there is a layer or a surface in which the filaments neither compress or nor lengthened or the extended. So you will see that the inner portion, this is the I am saying this is the inner portion, okay, is shortened, while this is the outer portion get elongated, extended. So this is the what when you're applying such a forces, you have a couple act, okay, that's a torque, and then you have a such a kinds of a bending. But remember that there are the some inner lamina, or you say the surfaces where the what these two forces get balanced, okay, and that's the what we called as a that's what we say that there the layer or a surface in which neither be a compression nor be a extension over there, okay, and that's the surface is called as a neutral surface. Remember, so neutral surface here I'm talking about that surface where the what there is an balance of your contraction, compression, or you say that length extension, okay, and that's the dash portion you see over here in this particular beam A B C D. E F represents the this geometrical figure, this particular geometry, you can say that this EF is a neutral surface, okay, that lamin, that particular filament is not having the uh, I mean to say it's balancing that compression and extension. So you have a neutral surface over there, and that's the what we called as that particular axis, okay, or a section by the plane of bending which is perpendicular to it, and that is perpendicular to it, okay, and that's the plane we called it as neutral axis, okay, and that particular axis we called it as the neutral axis. So here 3-4 definitions we need to remember, because this is the particular elasticity chapter we are learning bending of beam, and this bending of beam is very important to study some of the elastic constant, measurement of the elastic constant also, okay. So we will see that one. So here you can talk about those beams bending moment, and this particular neutral surface we define now, and we defined also the plane perpendicular to a perpendicular plane for which this EF is neutral, that we call that as a neutral axis, okay. So this some terminology we have been new for you, but okay, you will understand this particular. We are going to derive the expression for this particular bending moment. So here, in this particular geometry, you will see that the neutral surface becomes a plane surface, and the filament of this unstrained or unstretched layer that we called the neutral layer lying in the plane of symmetry of the bent beam, and we called it as a neutral filament. So names of neutral filament, neutral beam, a neutral surface, neutral axis, okay, this neutral name you called it as what, the plane the perpendicular plane which the what where the what this compression and the extension get balanced, and that's the particular of the beam, okay, what the beam I'm saying here A B C D, and that EF is the surface, is a neutral surface of the filament, that EF we called as a neutral filament, okay. The change in the length of any filament proportional to the distance from the neutral surface. So change in the length of any filament is proportional to the distance from the neutral. So whenever you have some extension, so suppose this is the AB is a extended portion and CD is a shortened portion you have, okay. So CD's shortening means goes on decreasing, and EA goes on increasing. That increment, okay, is we need to measure or proportional to the what we say the that particular change in the length, okay, that is proportional to the what, the distance that we measured from the neutral surface. So you understand now this particular figure A B C D E F, and that this dash portion over here it is representing, and that's dash portion, that's the axis neutral sorry neutral filament layer, and where this particular what we say the displacement. So suppose you have some other filament over to or upper to this neutral filament EF you called, okay. So here we need to determine how much bending is occur, what is the bending moment, how to measure this or how to determine the magnitude of this bending moment. We need to do that. For that so consider over here the change in the length of any filament. So here suppose you have consider AB is the length over there, okay, of this neutral surface, and there will be a change, and that change will be a AA prime over there, okay. So that means what, you have a BB prime. So AB prime on the what, some other filament, A prime B prime, sorry, that A prime B prime will be the what, another change, but that change from the center is, or we will say that from the center portion, or the uh, uh, where this curvature get bends, what we say the center of curvature, or the circular arc, okay, where this get bend, that radius, okay, that is important over here. So consider over here a small part of that beam, and here we consider A prime, A prime B prime, and AB, that's a small portion of the this particular curve or arc, you say. They form a arc, okay, and they subtend an angle theta over at the center of this curvature, which is a place at the point O over here. And let capital R be the radius of the curvature, and this part of the neutral axis, that what we have A prime B prime, be an element which is at place at a distance Z from the neutral axis. So you have a neutral axis over here, AB we consider a small portion, and A prime B prime will be the what, the changing one, okay, and which is at the place of a distance Z from the what, the neutral surface. So what is this A prime B prime, which is actually the, if you have a AB as a neutral surface, so radius of curvature you define as a R subtended angle theta, that arc you measured, whatever be the radius multiplied by the angle subtended by that arc, that is what actually your original length. But what is the change in length? Change in length will be A prime B prime, and that will be a what, this R plus this amount to be added, okay. Remember, this Z is uniform since we are considering very small portion of this particular beam, okay, and since the length is too large, remember that these shear stresses we need to neglect it in such a kind of I mean to say such a surfaces, okay, when we are talking about bending, okay. So this bending is happening over here, and this A prime B prime will be, you can write R plus Z into theta, and the original length you are writing AB is equal to R theta. So what will be the increment or a change? That change will be a definitely a prime B prime minus the original, that is AB. So you just do R plus Z theta minus of R of theta, that will give you the Z of theta. So this is the increment in the length of the filament, that is what you have a Z theta, okay, or you say change in the length. Since we are going above, so it will be always be an increment, okay. And since the original length of the filament is R theta, how we calculate the strain? Strain is nothing but a change divided by the original. So so that change is a Z theta, you have change, increment in the length of the filament, that you have just calculated as Z into theta, and original you have a R into theta. So Z by R, that expression comes, which is the expression for the strain, okay, or you say from this expression you can say that strain is proportional to the distance from the neutral axis, okay. So you can see that strain you defined over here, and the strain you calculated over here, that strain value which comes out to be a Z by R over here. So you can have this expression with you, okay. I mean to say, you can talk about this particular strain, it should be a proportional to the what, the distance from the neutral axis, because the expression comes Z upon R. R is the radius of curvature, and Z is the, that is the what, the increment, okay, or the length or the distance from the what, the neutral axis. So since there are no shearing stresses, we consider always, remember that, remember here there are no shearing stresses, so there will be a no change in a volume, no change in a shape and size of the body, remember that. So contractions and extensions of the filaments are purely due to the forces acting along the length of the filament. So whatever be the forces you apply over here, that acts along the length of the filaments, okay, that's not changing the what, the size and shape, or not changing any volume of such a body, remember. So these, whenever we are talking about such a forces, okay, or we say that such a contraction extension, which is always be a longitudinal one, okay, not like a shear one. Remember that, okay. So here I'm not taking this particular expression. Maybe we have, okay, yeah, we need to take that because the moment of inertia terms comes over here. So consider this small portion, rectangular portion over here, PQRS, you can see on your screen, and this is the particular section of the beam we consider, small portion of the beam, and this particular section at a right angle to its length and the plane of the bending, okay. And the forces acting on these filaments are always be a perpendicular forces, and the line MN lines on the what, this neutral surface. So this particular geometry I'm talking about, this particular shape PQRS, okay, we just consider a small portion where the what, that whatever be the forces you apply, okay, then that small portion that will always be a perpendicular to this particular section. So like you have equilibrium surface already EF, okay, and those Mn lies on the what, this particular neutral surfaces, okay. So let consider here the geometry we need to take into consideration to determine how much changes. For that, this geometry is important. So let the breadth of the section is, now you have a PQ, which is defined as a breadth of this particular section, and QR is a what we say a small d, okay. So which is like depth, or we say you have a breadth, okay, like that, and you have a depth means like a thickness of it, okay. So QR is a small d and PQ is a small b over here. So forces producing elongations and contraction in these filaments act perpendicular to the upper and lower halves. Okay, which halves I'm talking about? This PQNM. So PQNM, this is the upper house, and the other one we have MNRS here. Okay, so these forces producing elongations, and so you know that I'm just applying those forces. So you have a elongation is on the upper portion or the upper faces, and the contraction which is the producing on the below or the lower house, okay, and that is what here designated PQRS and PQNM, PQNM, okay, and MNRS over there. So hope you understand this figure. So I'm talking about this particular rectangular cross section we consider, and the forces which are perpendicular to this section, but these forces get balanced in the upper portion, that is a PQNM, and the what, the lower portion what we call MNRS, okay. And their forces direction should be opposite, as we already mentioned here, okay. That's what the contraction and those extension. So upper portion is extended and the bottom portion is contracted, but these forces should play an equal and opposite over there, okay, being opposite to each other. So I hope you understand that particular figure. So we can consider a small area delta A about this particular point A. So here we consider a small portion, that is what the small cross-sectional portion of this area, okay, rectangular section, on from which we taken small portion which has a delta A, and that delta A which is placed at a distance small z, okay, and that is what we say a distance from the neutral surface, where we have a new surface over there or new filament over there. So which is at a place at a distance z from the neutral surface, the strain produced in the filament passing through this area will be a z by r. Look at, we already calculate the value of strain in the upper equations. You know that how we calculated. So that strain we calculated and comes out to be a z upon r. So here it is the what, the same thing. We consider a small area at the point A, which is at the place at a distance z from the neutral surface. We know its strain value, which that strain value comes out to be a that distance from the neutral surface divided by the radius of curvature, that is a capital R. So can we define the Young's modulus? Yes, we can define the Young's modulus, which is a longitudinal stress upon the longitudinal strain. Yes, so that is the ratio of stress to strain, which is another elastic constant. Can we define? Yes. So stress we define over here, y times strain. Y is the Young's modulus of the material, okay, that has been taken for making those beam, okay. It is a material property, remember that. Therefore, the stress about that particular point A should be how much? So y into z by r. Strain की value यहाँ पे add की है. Strain का value कितना है? Z by r. So we just multiply y with that z by r. So where y is the value of this Young's modulus of the material we already mentioned, and therefore you can write down the stress. Stress is nothing but a force acting on that unit, on that area we consider delta A over there. So small portion delta A, that area where that force is acting, that force per unit area you called as a stress, okay. And therefore you have to calculate the force, you just multiply this value with the area. So delta A multiply by y z r, this becomes your force, okay, force acting or acting on that small portion delta A. This derivation hope you understand. Therefore the moment, when you are talking about the moment of the force, okay, how much moment is acting, so I say about which line. So which line I'm talking about this equilibrium line or equilibrium surface Mn, okay. So that moment of this force should be defined as, okay, you already calculated delta I y z r, okay, and it should be multiplied with what, so you have a delta A z by r into y, you have to multiply with the z again. Why you multiply z here again? Because this is the moment of the force. You say couple, okay, this is the force into the what, the length, which length, okay, that get that couple is acting, okay. So here you need to write this particular moment or a couple of this particular force you have over here small z. So don't confuse. So z is multiply with that particular force, so that becomes a moment of this force. So therefore y delta A z square, it becomes a square of z here and divided by r, that expression of this moment of this particular force. So since this moments of these forces acting on both upper and lower portions or house means other portion, okay, of this section are in the same direction, the total moment of the forces acting on the filament in this particular PQRS is given by summation of all those moments of forces. So summation sign here, you can see the sigma, a particular summation sign, okay. This summation of y delta is z square by r. So y is Young's modulus, which is comes out to be of summation sign. Y, r is a radius of curvature, that also remains same, not which comes at constant. But what is the changing over there? That is what the cross sectional area delta A of that particular, and the what, the square of that small z. So remember, since we are considering over here the rectangular kind of a cross section, so typically how much is the geometrical moment of inertia, okay, that comes into a picture, okay. So this particular section we consider Mn, okay, and it has a geometrical moment of inertia. So how to calculate that geometrical moment of inertia, or you say that whether it is a rectangular or it is a circular one, typically depending upon the which cross sectional area you have, accordingly that moment of inertia. Because remember here, which has a, that is what you have a, why you called as a, has a definition, has a moment of inertia, because this is a which has a similar terminology as a moment of inertia, but here it is that moment of inertia, that Ig, which is coming over here. I will tell you in detail how this Ig or this geometrical moment of inertia is calculated. But just here this terminology you need to take in your mind is that this delta A, summation of delta A z square, is a geometrical moment of inertia of this particular section Mn, and which is AK square. Now A is the whole area of the surface PQRS and K is a radius of gyration about Mn. So Here we need to consider this delta A as a what, a small a, and this z square, which is a square of this all z, okay, becomes a what we say, uh, k over here. So k, small k is a radius of gyration. So don't, if you remember what we defined in the moment of inertia, okay, but here I'm talking about those equal distribution of masses and square of from the axis of rotation, that is the moment of inertia generally. But here I'm talking about this geometrical moment of inertia, which has the same figure as the what, that summation of delta z square. How it comes, I will let you know. Okay, so the moment of the forces about the Mn, which comes out to be a calculated y bar, and the summation of delta z square is replaced with the ak square. So your value becomes a yig divided by r. So y into ig divided by r is the moment of the forces about that equilibrium surface Mn. So hope you are understand up to this. Still you have some questions regarding this geometrical moment of inertia, but it will be a clear when we talk about in later, another 5-10 minutes. Okay, look at. So the balances of the couple of the moment M is called as a bending moment. Okay, this is what we call as a bending moment, and this bending moment is acting on the beam due to the load when the beam is in equilibrium. So there is a no resultant force acting on this area PQRS, and resultant moment about EF is perpendicular to Mn is also 0. So in other word, it is the moment of the stress set up in the beam or the moment of resistance to the bending. So it is like, you know, you apply those forces. So whatever be the resistance it offered by that particular material or that particular beam, okay, to that bending without breaking, you usually call this as a moment of resistance to the bending. Okay, and so this is the terminology used in a engineering practice. Okay, and is called as, and it is the nature of a couple. This is another name. So nature of couple, or only a couple can balance a couple. So just a couple is a word which is basically coming from the torque. Okay, moment of forces acting on the length. Okay, and those forces are perpendicular to that length. That's what this couple term comes over here. So hope you understand. Obviously, it acts in the plane of the bending and equal to the bending moment at the section due to the load, and this it is referred as a bending moment. Now we come to this definition. Now you have a clear. So this is the bending which is acts on the plane of bending. You say which get planes and acts on the plane of the bending. Okay, in plane we always say perpendicular to this particular surface. Okay, and this bending moment due to the load we called as a bending moment. Okay, so hope you understand this terminology of bending moment. Okay, so now the question comes, how you say that this mass is a geometrical cross section. So for that you need to take this derivation into consideration. So consider what I'm talking about, the mechanical moment of inertia of that particular lamina, okay, of some shape as a cross section. So here you on your screen you can see this particular figure. Okay, and this particular figure I'm talking here is what, the PQRS. Okay, that is same portion we consider rectangular portion. Okay, it has a shape as a rectangular cross section, and so you might be not confused over here why this mechanical moment of inertia comes over here. So for that we need to take the understanding about the moment of inertia. For that I think you just revisit the syllabus what we taught in a moment of inertia, but you hear the things you can just guess get it. So just imagine the section as a rectangular plate PQRS, and of a unit mass per unit area. Hmm? And then the area of the strip is AB. So here the area we consider of the strip is AB, of length small b. Okay, small b is its length, and breadth is a dz. Okay, so here you can see this portion. Okay, AB portion which has a length small b and it has a breadth is a dz. Dz, don't confuse, dz is a small portion of a small breadth you consider. Okay, so what will be its area? So you just multiply breadth with sorry, so you just multiply breadth with its length, so you will get area. So so what is therefore its mass? So here I am talking about the rectangular plate which has a unit mass per unit area. So unit mass, if you consider its mass, okay, mass per unit area, it has a unit mass per unit area. Okay, suppose I want to multiply, suppose I want to make a mass, so what I'll do, I just multiply by the area with the 1. So here B dz becomes its mass. Okay. So don't confuse. Okay. So suppose this is a rectangular plate of having a unit mass per unit area, but I want to write how much mass it contains. So it is equivalent to its area. So that is a B into dz. So hence the geometrical moment of inertia of the strip about this Mn, okay, will be how much? So that much mass it has B dz into a what? The square of the distance from that neutral surface or a neutral filament which is a positioned at Mn. Are you getting? So B dz into z square is a moment of inertia. How we define the moment of inertia? However, the masses are distributed with the from the square of the axis. So here it is like a axis of rotation is like a mn, and this z is a distance. So z square we need to make, and that we just multiply by that mass b dz. So b dz z square becomes a geometrical moment of inertia of this strip, and that's what is I suffix g. That symbol we written over here is a moment of inertia. Okay, so don't confuse. Okay, so why this moment of inertia term comes over here? So therefore the moment of inertia of the whole plate, if you want to consider about this neutral surface or the filament Mn, what you do, half portion, so upper portion and lower portion, that's what you must do a twice from the center d by 2. Okay, or if you don't want to write twice over there, you just integrate 0 to small d there. Okay, so since we are considering from the middle portion or the central or the neutral surface, we need to consider the upper and lower portion. That's what twice factor comes over there, and the integration we need to do from the limits, that is from the original 0 to the upper one and lower one is d by 2. Okay, so that is what we have to divide it, that depth d divided by 2. So hope you understand this integration. Z square का integration क्या होता है? Z cube by 3. Okay, and you just put the upper limit and you will calculate this geometrical cross sectional area, which is comes out to be a geometrical moment of inertia of this rectangular strip, which comes out to be a BD cube by 12 over here. So BD cube by 12 is the what? That's the value of the what? Geometrical moment of inertia IG. Now you ask me this question where this IG comes. So this is the what where this couple or the moment of forces or you say bending moment which comes. Okay, and that is what YIG, that AK square we considered earlier, that IG which is comes out to be a BD cube by 12 over there. Okay, and now again the some new terminology, some engineering terms comes over here. Remember that is all we are talking about the mechanical kind of material properties. So here the quantity, this particular Young's modulus, elastic constant multiplied by the geometrical cross-sectional moment of geometrical moment of inertia. What the term always is? Geometric moment of inertia. Okay, geometric moment of inertia. Since it is a strip rectangular, that's why it is a geometry. If it is a circular, it is a circular moment of inertia, cross section, typically depending upon. So YIG is equal to YAK square is called as a flexural rigidity of the beam. Okay, flexural rigidity of the beam. So don't worry. Here again, this new terminology comes, rigidity. Don't confuse with the modulus of rigidity. Modulus of rigidity is what when the forces you are applying are the tangential forces. Okay, along the what particular thing, but here the forces you are responsible are the perpendicular. So new terminology comes over here, since it is a multiplication of this moment of inertia with the y called as a flexural rigidity, and therefore the bending moment can be expressed as y by r into geometrical moment of inertia of this section. And that is what you have flexural rigidity divided by r. Okay, so this is the another definition we comes over here of the bending moment. So this bending moment is y upon r multiplied by the geometrical moment of inertia of the section. So that is a flexural rigidity divided by r over there. So y ak square, that is your flexural rigidity. That's what y into geometrical moment of inertia is your flexural rigidity, and flexural rigidity divided by the what we say the curvature has radius r, that's in the denominator. So whatever be the shape of the cross section of the beam you have, accordingly you will have this particular geometrical cross sectional area. So here I am talking about the AK square, which is comes out to be IG, which is a BD cube by 12. We just calculated, okay, right now. So this is the BD cube by 12 is a IG value over there. So therefore the bending moment of the rectangular cross section will be a y into BD cube by 12 divided by r, correct? So remember, this is we consider for the rectangular cross section. If you have a circular cross section, okay, then the value will be a change. Circular cross section के लिए कितना है? You have a circular cross section with a pi r square, and that radius of gyration square becomes r square by 4. Therefore, your geometrical circular cross sectional area. So IG here we have AK square by which is AK square, which comes out to be a pi r to the power 4 divided by 4, which comes out because of the circular cross section, okay, not a rectangular cross sections. Okay, therefore the bending of moment for the circular cross section, generally we have a disc. Okay, when we have a disc about its diameter, what is its cross section, we need to consider always a circular cross section for that particular disc. Therefore the bending moment for a circular cross section comes out to be a yr to the power 4 divided by 4r over here. This capital R and small r don't confuse. So this pi r square, you know that the cross sectional area of the circular portion, and that because of the radius of gyration k square, it becomes r to the r square to the power 4. Okay, and this bending moment for the circular cross section comes out to be a y into pi r to the power 4 divided by 4r. So here are the two expressions we have. Okay, one is for the shape of the cross section. If it is a rectangular, we have a bending moment for the rectangular cross section is y times bd cube by 12 divide 12r. R is the radius of curvature, b is the breadth, d is the thickness. Okay, remember, or the depth you say. But for the circular cross section, okay, you have a bending moment is y times pi r to the power 4 divided by 4r. So here we have studied actually the bending of moment with the rectangular cross section as well as for the circular cross section. But any one material at a one time we have to consider any one of that. Okay. So I'm not going into further details. So can we define, okay, here the bending moment as the what the expression for the bending moments that we define here at is what the bending moment we define m as a y ig by r, and which comes out to be module this particular y, okay, typically proportional to the Young's modulus, proportional to the moment of inertia, and inversely proportional to the radius of curvature. So more less and less radius of curvature you have, okay, greater and greater moment of inertia you have, bending moment you have. Okay, remember. So when you say that the bending moment is a large, okay, radius of curvature is a small for that. So that's the relation we derived, okay, here. And you can take it from the book of Mathur, okay, and that's what I just uh, uh, shown over here, this particular book, okay. and these pages I am taken from the Mathur DS Mathur book, and you can take directly as it is this the particular derivation when it comes for your examination. Okay. So the Poisson's ratio, you know that we already defined lateral strain to the longitudinal strain ratio is a Poisson's ratio. So the Z that you have a change, and that lateral means what? Perpendicular. I mean to say when you have a, just like you know when we stretch a wire, so its thickness goes on decreasing. So that is a lateral strain. Okay, that is what the diameter is going to be a change. So along when you are stretch it means we are increasing its length. Okay, so that is a longitudinal strain. So that longitudinal strain here in this case is a Z by R, but Z upon R prime is what we have the lateral strain. So R upon R prime, that is R is the original radius of curvature for that radius, what we say that is subtended at center, that arc, okay, you have, and that R prime is a change over there, that radius of curvature is going to be a change. So Poisson's ratio can be determined over here by how much radius of curvature is going to be a change. Okay, by knowing that radius of curvature you can also calculate the Poisson's ratio. So you are applying those forces, you know that those bending, okay, and twisting those forces in such a way that you know that here the what, when you are applying those forces to get those lateral strain to be developed, and if there is a lateral strain to be developed to the original longitudinal strain, we can define here this particular elastic constant called as a Poisson's ratio. Okay, so I'm not taking another term over here, cantilever and these things we will discuss later. Still you have some question on this bending moment, we can discuss. Okay, hope you are agree with the derivation. You can write to me if you have the points are not clear, but I can change the setting and take your questions here. Okay, just wait for a minute. Okay, you can unmute yourself and ask those questions.